Okay, so let's see how the growth model we developed in the last video can be used to describe the proliferation of cancer cells in a living host. So in this case, let's say X1 is the density of healthy cells, and X2 is the density of cancer cells. Okay, as you see here, the model retains the same structure as we had for the competition between E. coli and P. aeruginosa bacteria in a shared space. So this equation represents the scenario when the two types of cells feed on different nutrients, and therefore they only compete for space, or you can say they have abundance of nutrients or feed on different nutrients. So they only compete for space. So this may be a very strong assumption given the fact that the cancer cells are cells that need nutrients as healthy cells in the organ. But for the sake of arguments, let's just assume they only compete for volume or for space. So these two equations will represent how healthy cells and cancer cells can grow or proliferate and compete in a living host. So before we attempt to solve these equations, let's look at the equilibrium points. Okay, so the equilibrium points, as we have done it several times before, the equilibrium point are calculated when are reached when the derivatives are zero. Okay, so we can obtain the equilibrium point by solving the two algebraic equations on the right-hand side. So other than the 0, point, which is an obvious equilibrium point, but is trivial. So there's other 2-point equilibrium point. So this two equilibrium point actually represent two sort of opposite conditions. One is sort of this one is sort of like we call deadly condition, where there's no healthy cells left. So the cancer cell triumph. So this is a deadly condition. This one here is what we call a condition of a complete remission. That means no cancer cell survive. The X2 is 0. There's no cancer cell survives. Only the healthy cells remains. Okay, so these are just two ideal, like two extreme sort of conditions, but they're very important for cancer therapy because we want to, if this equilibrium point represent a total remission, the first one is it means the cancer cell triumphs. Okay. So there's another equilibrium point that we can solve, we can achieve by solving the two algebraic equations. So we have done this exercise before. So we can apply the very same steps we've done before for the competition model and show that the point by solving this one set of two algebra equations, we get a equilibrium point. We call X1 star and X2 star here. Okay, so and also we can use MATLAB symbolic calculations to get the same solution. So this scenario is represent like the it represents like cancer cells and healthy cells. They both coexist in the same host. Okay, so this represents the third scenario is when the two cells, healthy cells and cancer cells, coexist in the same host. So let's look at what happened. Let's look at what happened around the first two equilibrium points, which are clearly the most interesting ones for the sake of cancer therapy, because they will tell us what's going on, whether the cancer wins or the remission wins. So we're going to discuss the notion of stability of an equilibrium point. Okay, so what do I mean with stability? So I forgot to mention this. So for the first, we must have that for both populations, the rate, the loss rate S should be lower than the production rate. Okay, so that otherwise these are, otherwise you can see that these two equilibrium point becomes negative, means negative density. So that's just is unable to describe the proliferation process. So we have to make sure that the dying rate is less than the production rate for either healthy cells or cancer cells. So that's a sort of a condition just to make the physiological process relevant. Okay, so second, that's simplify the parameters in a way that is consistent with the process of cancer spreading or proliferation. Let's say the cancer cells and healthy cells have similar size, okay, so that alpha 1 and alpha 2 are both equals to 1. Okay, and also they have the same the saturation B are the same. So we call B1 and B2 are both equals to B, which is the saturation limit or the capacity limits for both cells. Also, let's say the cells dies at the same rate, just for the sake of simplify the problem, regardless of the nature, whether they do die in the same rate or not. But cancer cells in R2 bigger than R1 means cancer cells reproduce at a faster rate than healthy cells. Okay, means cancer cells proliferate faster. So that is the case for for cancer, because the cancer spread faster. So this is sort of like assumptions that we make to simplify, to tailor to the cancer growth model. So now there's two equations. After we apply these assumptions, then we can simplify as this a systems a set of two differential equations, and then the two equilibrium point here, and simplified as this as the two equilibrium point. Okay. So let's look at the so let's say that let's first examine the equilibrium point number 1, the first equilibrium point. So the first equilibrium point represent what? Represent the maximum. The first equilibrium point means the healthy cells has a density of 0, and cancer cells, this is has an equilibrium density, has an equilibrium density of this. That means has a maximum sort of cancer proliferations. There's no healthy cell left. So now we're going to examine whether this equilibrium is a stable condition. So how to examine whether it's stable is we are going to provide a small perturbation. Okay. Or for example, such as like a small amount of healthy cells in the system to see whether they would do anything at all. Okay, so we are going to provide a little small perturbation we call epsilon. Epsilon is positive. For X1, means we'll put a small amount of bulk of healthy cells into the organ, okay, to see whether the physiological process leads to a solution that that sort of attract back to the equilibrium or move away from the equilibrium. So if solution representing the physiological process returns to the equilibrium after this perturbation, then the equilibrium is stable. If the physiological process move away, the solution representing physiological process moves away from the equilibrium, then the equilibrium is unstable. So what we're going to do here, so we're going to do the derivative of x1 around the equilibrium point, when we give a little small perturbation for x1, we call epsilon. Okay, so x1 equal to epsilon with a small perturbation. X2 is at equilibrium, Okay, so we apply these conditions into the solution, into the right-hand side. Okay, into the right-hand side. And we get this expression here. Notice that R2 is bigger than R1 because R2 is the cancer cell production rate. It's faster than the healthy cell production rate. So R2 is bigger than R1. So this term is negative. And this minor is another term, which is positive. So this whole epsilon is a positive value. So this whole expression is negative. That means the derivative of x1, okay, with regard to time, okay, is less than 0. That means x1 is going to decrease. Okay, it's going to decrease once you provide a small, okay, so if you provide a small perturbation of x1, and then x1 will decrease back to 0. Okay. So if we want that the density go back to the equilibrium value once the perturbation is over, as you can see, we need the derivative of x1 when x1 equal to epsilon is negative. It turned out to be is indeed negative. So a negative derivative, in fact, means that the density of x1 will decrease or will evolve back to the equilibrium point. Okay, so this means that we have so we can also look at so for any positive perturbation, no matter big or small, x1 will return to its equilibrium at x0. Okay. So this is satisfied for any perturbation epsilon. Okay. This means that no matter how small or large we choose the perturbation, the process will eventually get back to the equilibrium point. So when the equilibrium is stable, regardless how big the perturbation is, we say that this equilibrium is globally stable. We also can look at this graph here. We plot x1 against x2. Okay, the equilibrium point is represented by this red dot here. If we move it away, we provide a perturbation in a positive direction represented by this red arrow. Okay, and then because once x1 is bigger than 0, you can see dx1 dt smaller than 0 means it will go left. So as soon as it deviates from this equilibrium point, it will move back. It will return back to that equilibrium point. So that's why we say this equilibrium point to be globally stable, because no matter how big the perturbation is, it will return back to their equilibrium point. So what I'm saying here is that the equilibrium point represented by the triumph of the cancer is a globally stable equilibrium. It is an equilibrium towards which we might converge if the perturbation we apply are temporarily short or transient perturbations. So this captures an important aspect of the proliferation of cancer cells, provided that we do not kill completely the cancer cells after some cycles of treatment with that cancer, regrow, and then the regrowth process will eventually lead to the triumph of cancer. So what about the other equilibrium point? Second equilibrium point represent that the healthy cells actually wins in the end, and represent sort of like a total remission, that all the cancer cells are killed. So let's look at this equilibrium point representing the remission. So we can repeat the same process. We provide a positive small perturbation epsilon for x2 that deviate from the equilibrium. Okay, so then we look at this dx2 dt to see whether it's positive or negative. Okay, so we apply these conditions to the right-hand side. We get this expression here. We can see this expression is small, is positive. This one, because R2 is bigger than R1, so this is a positive value. The second term is also a positive value. So for a small epsilon, and this whole thing, okay, this entire expression is positive. That means if you move a little bit away, if you provide a small perturbation that deviate from their the equilibrium point for x2 equal to 0, and then the x2 will increase because because dx2 dt is bigger than 0, so it will increase. It will move away from the equilibrium point unless you provide a big enough epsilon here, and then that represents. So basically, there's a strip. You can see this red dotted line here represents sort of the epsilon value. It has to be in order below this dotted line, below this dashed line, the x2 will go, will increase. X2 will go increase. That means because x2 represents the density of the cancer cells. So the cancer cell, as long as you have a little bit of cancer cells, you introduce a little bit of cancer cells, it will grow, it will deviate. The cancer cell will not just die out right away. It will not die out, but it will deviate away from that equilibrium points. Okay. So in this case, we call that the equilibrium point for this equilibrium point for healthy cell wins, the condition is an unstable condition. Okay, so because any perturbation in this strip here, any perturbation in this strip here will push the solution away from the equilibrium. Okay, so we shall conclude that the remission state is an unstable condition. So it is a condition from which we can easily escape, unless we force the physiological process of cancer proliferation to stop by either, say, doing some kind of cancer therapy, like a chemo or some other therapy or treatment. Otherwise, if you introduce a perturbation, that means you introduce some of the cancer cells back. If you have a remission, you think the cancer cell sort of are killed, but if there's a little bit of cancer cell remains, that means a little perturbation there, it will move away from this equilibrium. Okay, so that's why the cancer therapy is hard, because their remission is considered not a stable equilibrium. Okay. So what about a third? What about a third point? So what about the third equilibrium point we talked about earlier? So it turned out to be the third point is actually not really very relevant, because third point means there are healthy cells. There's healthy cells in the organ. There's cancer cells in the organ. They coexist. Okay, they coexist. So provided the condition we have earlier, like we assume alpha 1 equals alpha 2, you can see when alpha 1 equals alpha 2, you are dividing a 0. So which means the cancer, well, it's sort of like this whole a model is undefined. Okay, it's undefined. You can see it's. So you can see that, so this is sort of represent this kind of what this means. it means that cancer cells and healthy cells just cannot coexist peacefully in the hosting organism. Okay, so this means it doesn't coexist, but you can also look at some other conditions. What about alpha 1 and alpha 2 are different? They're not one. There's between 0 and 1. You actually can find some of the other solutions, but I'm not going to talk about here. Okay. So what is our conclusion? And our conclusion for this one is, so we use the same, okay, we use their bioreactor equations that we developed from module 1. We modify that, okay, and then we model another process with some other physiological process, such as the, competitions between two bacteria or competition between cancer cells and healthy cells. They can compete for nutrients, or they can compete for space, or both. Okay, so we can recap what we have learned here. We have learned there is a class of models that can be used to describe any type of process that involves logistic growth. So we call this sort of like a model template we can use for a variety of models, involve similar kind of mathematically, they have similarities. Okay, so this class of models adapts to different problems and can be conveniently modified to account for the competition between two or more populations, as well as to determine whether there may be an equilibrium at which all populations coexist, either in a stable way or unstable way. Okay, so this is important to, from this we learn about stability. We're gonna talk more about stability in more of a dynamic way next time when we talk about some other sort of approach to examine stability. Okay, so this concludes the presentation, conclude this module.